Welcome to 32nd session on measure theory, and I think this is the fifth or sixth session on LP spaces. And as I said at the end of the last session, today we will be talking about L in infinity space, which is essentially bounded function. We will explain all these things. We will prove complete result. Okay, probably within about 45 minutes I should be able to do it. Let us hope so. And of course, I will depend that you had gone through some of my analysis lectures where I had proved about uniform convergence, etc. If you had understood, then you will see that analysis is exactly similar, easier, etc. Okay. So it's always good to learn things thoroughly, not from an exam point of view. Am I repeating this too much? So let us dotted screens sharing, yes. So let us fix a measure space. What we want to talk about is functions from maybe extended real number system or C, okay, in some sense bounded. Okay, we know what is meant by bounded function. That means if I say f is bounded, implies there exists a positive, so that for every x in x we should have mod of x should be less than or equal to m, right? But as you have learned when you dealt with the L1 spaces, etc., okay, if f and g are equal almost everywhere with respect to the measure mu, okay, we should like to identify them. You understand what I'm saying? Therefore, the boundedness we have to be careful. Let us look at an example to make sure that you understand. So let us look at f to be the characteristic function of q. Okay, no, sorry, let me not modify. Fx equal to 0 if x is not in q, and equal to x if x is in q. Right? Now, do you see that f is not bounded? Because n is in q, therefore fx equal to n, as x varies, f at n equal to, right? Therefore it's not bounded. On the other hand, let us look at if I am ready to ignore this set which is of measure 0, then it's actually bounded. By 0. What does that mean? That means, okay, so when I say f is bounded essentially by, okay, I want to say f is bounded essentially. What does that mean? So I have x, I have this set to E, and this mu of E is 0, right? Then everywhere else, these are all points, very good. So I can find an m positive, so that whenever x is not in E, then mod f x is less than or equal to m. You understand that? So I will be ready to ignore a set of measure 0. So let us write the definition carefully. So I say f is essentially bounded if there exists m positive and a measurable set E in B with mu of B equal to 0, such that for all x not in E, we have mod f x is less than or equal to m. A typical example you should keep in mind is this. This is the most typical example. Yeah, is that clear? Keep this picture also in mind. It should be clear. So pause, review, proceed. If such a case, then we say M is an essential bound. For F. So when do I say M is an essential bound for F? This means there exists E in B with the mu of B equal to 0. 1, mu of B must be 0. 2, for all x not in E, mod fx is less than or equal to M. I'm just repeating. Okay? Right? Okay. Now, let us go back to the earlier example. Okay? Notice that this may not be unique, but there is something very interesting happening. Let me just look at example. Okay? I modify the earlier example. Okay? F from R to R, of course, our spaces R, M, and M. The big measure space, right? And let me say F at square root 2 is 10 to the power 2000, and Fx equal to 0 if x is not cube and x is not equal to square root 2, and Fx equal to 1 if x is in cube. You understand this? Now, if you say, if I take E equal to Q, then if x is not in Q, you cannot say 0 is an essential bound. It's not an essential bound. I will write it as ESB. Okay? Because this number is there. But I can, instead of E, I can take E to be Q union square root 2. Right? Then 0 is an essential bound. So do you understand that? So, right? Let us recall how did we define LUB. Okay? If F is from, let us say, R to R, I say M is an upper bound. Okay? If Fx is less than or equal to M for all x in R. Right? Then, what do I want is the, in some sense, the minimum of all these things. That is, I want the LUB, least upper bound. That is, you are looking at all M, where M is an upper bound of F, and look at the infimum of this. Okay? That is what we call the least upper bound. Yeah? So pause, review, proceed. So this suggests how to find the essential supremum of an essentially bounded function. Okay? So again, as though to do all these things, I can take f to be any function, but since we are in measure theory, we will always assume measurable. I did not mention, but hereafter when I say, I will think of it as a measurable function. Okay, but this concept boundedness, essential bounds, work through. Okay, hold for any function. But our interest is only to look at class of measurable functions, right? Okay, so how do I define essential supremum? That is, so what is the thing I have to do? So first let f x be mu to wherever it is re or C or R be essentially bounded. This we already defined. Right? That means there is at least one M which is an positive, which is an essential bound. For right? So what I am looking for, the essential supremum of F to be the GLB of this, the infimum of these things. M, that is M is an essential bound. Okay. So please pause and review. Pause. Review this and compare with the notion of supremum or LUB, then proceed. Just 1 second. I will control the speed of the pen. All right. Is that clear? Okay. So we want to say, define L infinity to be the equivalent class of measurable functions before defining, let us also observe one more thing. Suppose F is essentially bounded. And F is equivalent to G. That is, F equal to G almost everywhere with respect to the measure mu. Right? Then I want to say G is also essentially bounded. That is very clear because when F equal to G almost everywhere with respect to mu, that means there exists a set A which is in B, mu of A equal to 0, and for all x not in A, Fx equal to Gx. Right? Now if F is essentially bounded, means there is an M positive and a set E in B such that mu of E is 0, and for x not in E, modulus Fx is less than or equal to M. Right? Now I want to say G is essentially bounded. Do you see how? Because now take A union E and suppose x is not here. Since x is not in A, mod of Gx is same as mod of x. But x is not in E, therefore it is less than or equal to M. Right? And since A is of measure 0, E is of measure 0, call this as B, then mu of B is measure 0. Therefore G is essentially bounded. Okay? Pause, review, proceed. So now I can talk about L infinity. L infinity is the class of measurable functions, and F is measurable and F is essentially bounded. Right? Now L infinity of x, the mu, is the equivalence classes. Okay? Right? Now I claim this is a vector space. These are all easy because F, I have some, let us call it as a C, C1 and E1, F1 and F2, C2, U2. Do you understand what it means? This is an essential bound. This is the exceptional set. Okay. Therefore, F1 plus F2, if X is not in U1 union U2, as we did earlier, right? And these are set of measure 0, and these are bound. Therefore, this is an essential bound for F1 plus F2, and so on. Okay. So this is a vector space. Okay. Notice that when I want to say it's a vector space, I am actually starting with F1 in L infinity and F2 in L infinity. And as we saw earlier, it does not matter which representative I take. Now I have a map. I want to define a norm on that. Remember, this again is equivalence class, but as we have accepted, we will not write it. I define this to be the essential supremum of F. So we claim this is a norm. Okay. Almost all is easy. Okay. It is very clear, ma. Okay, this is called L infinity norm. After I prove it's a norm. Okay. This is greater than or equal to 0. Suppose it is 0. Okay. Does it imply F is, what do you have to check now? It's a function of L infinity, therefore it is 0 almost everywhere. This is the question. So, does this imply that? Okay. That is very easy, right? If this is 0, what does it mean? There is a set U in B, mu of E is 0, and for all x not in E, mod fx is, mod fx is 0. That means fx is 0 for all x not in E, right? And what is the exceptional set? E is a measure 0, therefore f is 0 almost everywhere. Follows, right? So the rest of the things are very easy. We had actually proved it here. So this is a norm. It's clear. Okay. Pause. Proceed. So this open is a norm on the vector space. Okay. Okay. Now what we want to prove? We want to prove this we had absolutely observed, but let us just quickly say that suppose, remember, see, if my x equal to r, that is x b mu equal to r m m, and we know that CC infinity of r is contained in L infinity. Again, remember, what does this mean? This f I am going to take as equivalence class of f. And again, we remember that in the equivalence class, there is a, if at all, there exists at most one continuous function. That is, there cannot be two continuous functions here. Okay. If G and F is continuous, then G is unique. We had already seen this. Please watch that. Okay. So now let us see what does it mean to say F1 converge to F. Assume that F1 is or not C infinity, CC, continuous. Okay, FR and CC of R. Okay, with respect to norm. This means norm of Fn minus F, the L infinity norm goes to 0, or limit of that is 0. What is the meaning? right? Let us understand. So, what does this actually mean when I say the F1 converges to this? Okay, this again, the convergence is almost everywhere. Okay, so if F1 converges to F in this norm, okay, let us assume ENs are the exceptional sets for the function Fn, right? And this convergence also almost everywhere. That means let E be the exceptional set for the convergence. That is for all x in x minus E, Fn of x converge to Fx. Okay, that's all we mean. Is that okay? We can say something more, but don't worry about that. Is this clear? Yeah. So what does it mean to say this? This means if you give me an epsilon positive, there exists a natural number n, so that for all k greater than or equal to n, fk of minus f in L norm is less than epsilon, right? This means for x not in E, fk of x minus f of x in modulus is less than epsilon for all x, that is for all x in x minus E, right? Notice that this is nothing other than uniform convergence on the set x minus E. So pause, review, proceed. If either you have read from my book on metric spaces or watch my videos on metric spaces, I would have defined this L infinity norm or sup norm. I would have defined in the space of continuous function if F1 converges to F in the L infinity norm or sup norm, if and only if F1 converges to F uniformly on the set. Okay, that's what we are essentially proving here. Okay, right. This is just to say. Okay, let's now continue. So similarly, when do I say F1 in infinity is a Cauchy sequence? Sequence in L infinity with essential, this L infinity norm or essential supremum norm. Okay, what does it mean to say it's a Cauchy? Again, if it is Cauchy, what does it mean? For every epsilon greater than 0, there exists an n, so that for all m and n greater than or equal to n, the subnorm of Fn minus Fm is less than epsilon. The not subnorm, L infinity norm. Okay, by the way, if F is in L infinity, this you don't read as subnorm because it may not be subnorm. Let us look at the very first example. F is 0, x is not in Q, equal to x is in Q. Okay, so the subnorm of F is 0. The subnorm of F is infinity. Let me write this way. That's why I write it. Subnorm of this is infinity, whereas L infinity norm is 0. Okay, maybe one should make a remark because these are the small things students don't get time to reflect upon. Okay, if f is a function from x to r, let us assume x is bm. Okay, there are two notions. I can define this and I also can define sub. Okay, this I can define only if f is bounded, because what is this by definition? This is supremum of mod fx. Mod fx as x varies over x, whereas this is essential supremum, right? I may be able to omit a set of measure 0 outside which this will be supremum. Do you understand this? Okay. Now there is one more point. These are the small points which I want to say, which is never emphasized. I explained carefully. Okay, if you want to be comfortable, you should go through all these things. Now let us look at, if f is in L infinity, I define this, right? This is a number. I'm saying this is an essential bound. What does this mean? This notice that this is by definition infimum of m, where m is an essential bound. Right? So when I say this is an essential bound, that means this fellow has to be called this as I said some essential bound, right? em, e for essential, m for bound. Okay, that belongs to em. Okay, that means this is a minimum. This set has a minimum. Em has a minimum. Namely, are you following? These are the subtle things. It's always good to learn such things. This is how one develops one's critical thinking. Okay. Why? That means what I have to show? To prove this, okay, call this as C so that I don't know to write this much, okay, is an essential bound. Okay. To show this, what I have to say? I have to find a subset E in B so that mu of E is 0, and for all x not in E, modulus fx is less than or equal to C. Is that clear? Right. Now let's look at the picture. This is my C, right? Remember, if you have gone through my real analysis book or real analysis, I many times say the only way to make use of LUB or GLB, that is one of the reasons I don't like to use infimum supremum. Okay, use to say if C, remember this is an essential bound. So this is the GLB. It is the greatest lower bound. Among all lower bound, this is the greatest lower bound. That means anything greater than that is not a lower bound. It is the greatest lower bound, right? Therefore, C plus 1 by n is not a lower bound. Okay, for all natural number n, C plus 1 by n is not a lower bound for the set em. Okay, that is, what is em? The set of all essential bounds. Okay, maybe I should have used EB. Anyway, it's all right. Now that I have written, right? That means what? There exists an alpha n. That means there exists alpha n in EM. So that, okay, this is a greatest lower bound. Therefore, C will be less than or equal to alpha n. But this alpha n will be strictly less than 1 by n. Do you understand this? Right? Now, since alpha n is an essential bound, there exists an En in B, so that mu of En is 0. And for all x not in En, what do I have? Modulus fx is less than or equal to alpha n. Right? Very good. Now let us look at E to be the union of En. Right? Suppose x is not in E. Then what does it mean? My fx is less than or equal to alpha n because it's not in En. But alpha n is less than or equal to m plus 1 by n. Therefore, for all x not in E, I have this. Fx is less than or equal to m plus 1 by n. What does that mean? This means for all x not in E, mod fx is less than or equal to m. And notice that countable union of sets of measure 0, therefore mu of E is 0. Therefore, m is an essential bound. I wrote as C perhaps. Okay, so C plus 1 by n. Did I draw a picture correctly? Yeah, right. Okay, so we proved the result. Or review proceed. We now come to the important result. When I have Fn a sequence in L infinity, what do I mean by Fn is Cauchy with respect to this norm. Okay, as I said earlier, it's very clear. Okay, what is the definition of this? For every epsilon greater than 0, there is an n, so that for all m n greater than or equal to n, modulus, okay, norm of Fn minus Fm, the L infinity norm is less than epsilon. That means, this means if epsilon is an essential bound for Fn minus Fm. That means there exists En m, which is measurable. Mu of En m is 0, and for all x not in En m, we have mod Fn of x minus Fm of x is less than epsilon. Do you understand this? Right? Now let's E equal to E n m, where n and m vary over natural numbers. This is a countable set, therefore the E is countable union measurable set, therefore it is there, and its measure is also 0. Right? Each of the sets is measure 0. Countable union measurable sets is again measurable, and countable union sets of measure 0 is again measure 0. Okay, so we have got it. Right? Therefore, what do you think I have? For x not in G, for all n and m greater than or equal to capital N, I have mod Fn x minus Fm x is less than epsilon. Do you follow this? That means the sequence Fn is uniformly Cauchy. Is it on all of x? No, on x minus e. So when I say Fn is Cauchy in L infinity norm, that means Fn is uniformly Cauchy on x minus a set of measures 0. Is uniformly Cauchy on the complement of a set of measures 0. Is that clear? Or review proceed. Now we are ready to prove the theorem. The space L infinity x p mu is complete. This is the measure space with respect to, so let me write it, because when I say complete, the measure, the metric or the norm should be said. This is the L infinity norm is complete. Okay. The proof is easy. It will use what I usually call as curly leaf trick. Okay. So let us give proof. So let Fn be Cauchy. Right? Then we know, okay, Fn is uniformly Cauchy on x minus e, where e is in b, measure of b is 0. There exists something, right? We had already seen that. That means for each x not in this, Fn of x is a Cauchy sequence either in R or in C, depending upon you are dealing with complex numbers or real numbers, right? Therefore, any Cauchy R or C is complete. Therefore, there exists alpha x, a real or complex number, so that upon x converges to alpha x, where this is for all x not in. Okay, so I define a function f of x equal to alpha x if x is not in E and equal to 0. Then f is measurable because x minus E is measurable set and fn's are measurable functions. Therefore, the converge point wise to f on this set. Therefore, it's measurable. Okay, on the complement I am defining it to be 0. Therefore, we had already seen such results. This is measurable. Okay. More generally, there is a glowing lemma, right? Suppose xb is a measurable space. Okay, write x as, let us say, a union b, a, b are in b, measurable, and this is a disjoint union, right? And suppose f from a to somewhere is measurable and g from b to measurable, then define phi of x to be fx if x is in a and equal to gx if x is in b, then pi is measurable. Okay, this is a very easy one. I don't remember whether I have done it when we dealt with measurable function. This is like a glowing lemma. The proof is easy. Try to work it out on your own. I'll just give you a picture to make you understand what is happening. So this is my x. Okay, so this is my a. So this is my a and this is my b. So if I take something f greater than alpha, okay, what will it be? It will be something like this. I'll use a different color so that which color will be useful. Okay, if phi greater than alpha, I have to say this is a measurable set, but phi greater than alpha, I can write it as x in a such that phi of x is greater than alpha and union x in b, phi of x is greater than alpha. But here it is f, here this is g, and f and g are measurable. Therefore, this is measurable. Measurable union of measurable set is measurable. Therefore, this is measurable. So, did you see what I did? This is what I want you to think about. So, whenever you have something, okay, if you think you know it, you had already seen it, quickly go through the proof. Okay, for example, I don't remember whether this glowing lemma I proved in measurable set when we talked about measurable functions. But the thing is very obvious, so I thought let me do it here. Suppose I have done it, then also I will quickly go through the proof. Okay, make it a habit. This will make your life easier. Okay, good. So finally, what you have done is, let us go back to our color. So f and Cauchy. Okay, E is a set. Okay, so that f is uniformly Cauchy on x minus e. Then we found out on x minus e, f and converges to f uniformly. Right? So we extended that function. Okay, that is f of x equal to limit of f1 of x if x is not in e, otherwise 0. Then f is measurable. Okay. Next thing I want to say is f belongs to L infinity. That is, f is essentially bounded. Once I have proved that, the next thing I would like to say is f and converge to f in L infinity. That means mod f1 minus f infinite norm goes to 0. Okay, these are two things I would like to prove. Then I would have proved if the L infinity space is the space of essentially bounded function with respect to the L infinity norm is a complete metric space. If you know functional analysis, it means it's a Banach space. Okay, this is what you want to prove. This essential boundedness is easy. Suppose x is not in E, if x is in E also it's 0, no problem, right? So let us start with x not in E, that will be easier because if x is in E, then fx is 0. Therefore, nothing to worry. If x is not in E, let us look at mod fx, I have to bound. Okay, I have to whether there exists some constant c so that I equal to c for all x not in E. Then it will be essentially bounded, right? So how do I find that? This is why I said if you have gone through my videos on uniform convergence or analysis book on where I talked about point-wise uniform convergence, you will be confident how to do these things. So I want to estimate, the only way I know is fx is the limit of fnx, right? So this fellow mod fx is less than or equal to fx plus fnx. This is clear? This is for all x not in E. Forget this, I am looking at this. X not in E. Right? Now since f1 is Cauchy, uniformly Cauchy on x minus E, okay, for epsilon equal to 1, there is a natural number n, so that mod fn minus fm in L infinity norm is less than 1. Okay, we had already seen this means for all x not in E, that means mod fn of x minus fm of x is less than 1. Yeah, okay, right? So how do I do that now? So for all x not in this happens. Okay, right? Okay. So I'll just do this for the time being, letting m tend to infinity. Okay, that means mod fn of x minus f of x is less than or equal to 1. Right? Therefore, this will be for all n greater than or equal to n, modulus f x will be less than or equal to modulus f x minus fn of x plus fn of x. Is it okay? Right. Is that clear? So this fellow, therefore this will be less than 1 plus supremum of L infinity norm of fn. This is for all x not in E. Therefore 1 plus is an essential bound. Okay, right. There are other ways of proving this. This letting n tend to infinity, I could use a curry leaf trick here. Right? But I skip it. Okay, this is the book proof you will see in many books, so you can assume. Okay, but I will again do that below. Therefore, I know the limit function belongs to L infinity. Therefore, I have to prove 2. That is f1 minus f in L infinity now goes to 0. Right? Let us again go back. So I have to estimate mod fn of x minus f of x. So this is for x is not in E again. Because if I show this, if I found a bound, notice that this is a measure 0. If I show this less than epsilon for all n greater than or equal to some n, okay, then that means the essential bound for this is epsilon. Are you following? If I show there exists n so that for all x not in E and for all n greater than or equal to n, modulus of fn x, let me write modulus of fx minus fn x is less than epsilon. That means epsilon is an essential bound for f minus or f minus fn whenever n is greater than or equal to n, right? That means f minus fn is less than epsilon. So we would have proved it. Okay. Right. So let us try to estimate that. Now I have fx minus fn of x. Right? And again let us recall x is not in E. Okay, go through the proof. You can modify this to prove, to show this portion. You can avoid this. Okay. Please, that is why if you have gone through my uniform convergence, you will understand. Even otherwise, this proof is very good. There is no problem. Okay, there is no issue about the proof. Okay, this is what I want to do. Right? Now, how do I estimate this? So I want to say, okay. Now notice that fn is Cauchy, right? Therefore, for the given epsilon, okay, given epsilon, there is a natural number n such that mod of fn minus fm in L phenomenon less than epsilon. That is, epsilon is an essential bound for fn minus fm for all n and m greater than or equal to n. I'm just rephrasing, saying the same thing in different words, right? Okay, so that is what I want to use. This is what you use a curly leaf trick. Okay, suppose let's look at the triangle inequality. It says if xy is in X where xd is symmetric space, okay, I want to show distance between x and y is less than something. Okay, I want a good estimate. What it says is find any z, find z in x such that distance between x and y is less than or equal to. This is true for every z, so that this becomes small. Okay, this is true for every z, but you try, if you want a better estimate for this, you have to find a smart z. Okay, this is the basic principle behind what I call curly leaf trick. Therefore, fx minus fn x. Okay, now notice that fn x converges to fx, right? Therefore, there exists for this epsilon given here, okay, there exists an nx which depends on x such that for all n greater than or equal to nx, mod fn of x, mod fx minus fn of x is less than epsilon or epsilon by 2. Do you understand this? Make it epsilon by 3. I do not know which one I want. Okay, right? So now I'm going to use that. Now I have f of x minus fn of x, okay, is less than or equal to f of x minus fn x of x plus fn x. If you don't want to call this m of x. There exists m of x so that for all n greater than or equal to mx, mod fx minus fn x is less than epsilon by 3. Okay, so for the given epsilon I have this fn x. Then let us look at fn x minus fn of x. Right, so you follow that. Now I know this is less than epsilon by epsilon by 2 is good enough, epsilon by 2, but I want to make sure this is less than epsilon by 2. For that, what I have to assume? I have to assume my nx, my mx should also be greater than n. Remember this, for all x not equal to E, this is a true statement. Go back. Fn is Cauchy, therefore for all x not equal to E, These are true. Mod fn of x minus fm of x is less than epsilon or epsilon by 3 for all x not in E. This is what it meant by Cauchy in L infinity, right? So let us go back. So I choose m which is greater than my mx and also greater than n. That means choose m which is greater than or equal to maximum of mx and n. Okay, this m is fixed, right? Therefore, mod fx minus fn x is less than or equal to mod fx minus fm of x plus mod fm of x minus fn of x. Okay, this is like your z. Okay, distance between x and y is less than or equal to x and z plus distance between z and y. And now I choose z carefully. For this particular number, you are keeping x not in E. For this thing, I have found it, right? And if therefore, if n is greater than or equal to capital N, you understand, that's all I need. Okay, this is less than epsilon by 2. This is less than epsilon by 2. Therefore, this is less than epsilon by 2. This is true for all n greater than or equal to m. Therefore, what I have shown is fn of a fn converges to f uniformly on x minus e. And in particular, fn converges to f L supremum. Sorry, L infinity now. So, go through the proof, okay? And of course, needless to say, if you have gone through my lectures on uniform convergence, it would have been much easier, okay? But if you have not missed much, except you may have to spend a little more time, revise it twice, then you will find it easy. As usual, please discuss with your friends, okay? And that's about 53 minutes. I think it's time to stop. There is something which I wanted to say. I wanted to say there exists no countable density in L infinity. Okay, but usually when it goes to functional analysis, you need such things. Let us hope somewhere something will be done. Okay, I hope you enjoyed. So this completes something to with L infinity. So next session will be on L2. I have to define what is L2, of course. Okay, after that I will talk about LP. Okay, so I may need 2 or 3 more sessions. So all the things about LP spaces will be complete. Okay, I hope you enjoyed. It is, I know for some of you it might have been tough going. Okay, my sincere advice is once the exam, semester break, etc., please go through real analysis carefully. Okay, look at the sequences and uniform convergence section in my book or in my videos, and that will teach you a lot of analysis. That is more than enough for you. Okay, in case you just somehow passed real analysis but you are not confident about that, please do that during semester breaks. Okay, take care, we will meet again.